All right. Hello and welcome everybody to episode 8 of Technically Speaking. Particularly excited about today's presentation because this is one of my favorite things to talk through is the area of psychrometrics. I think it's a really critical element to what we do in water damage mitigation and really puts the professionalism in the decision-making process behind mitigation and drying structures. So with that, let's go ahead and kind of roll into things. As with each Technically Speaking episode, my name is Brandon Burton. I am the Senior Principal of Customer and Industry Relations at CoreLogic, and also the Chair of the ANSI and ICRC standards. A couple of quick housekeeping things as we go in. First of all, for those of you who are returning, you know that we don't use the chat during the webinars, but we do use the Q&A. So please, as we're going through the presentation here today, don't hesitate to drop any questions that you have into the Q&A tool. I will see those questions enter as we go through the webinar, and I may jump on them at that moment if it makes sense where I'm at. But most of the questions I'm going to handle at the very end of the webinar. And it doesn't matter to me what you ask about. Anything water damage mitigation or industry related is fair game, even if it has nothing to do with the topic that we're talking about today. Those Q&A sessions are a lot of fun. So make sure that you do drop your questions in as soon as you've got them so you don't lose them. So with that, let's go ahead and roll in and get things started. So with today's presentation, I'm going to give you kind of an overview of psychrometry, starting with the basics, and then move into some more in-depth psychrometry. So today's presentation is really going to be targeted not only at those of you who are using psychrometry every day, but also if psychrometry is kind of a foreign language to you. You're still going to get a lot out of today's presentation. You'll walk away from today with a couple of really basic questions answered. The first and foremost is, what is psychrometry? And just what is this thing called psychrometrics? The second thing that's really important to me is I want to make sure we understand why psychrometry is important to me, and me being any of the stakeholders in the mitigation process, whether you're the technician, the project manager, the business owner, the claims adjuster, the property owner. Psychrometry is a value add or a benefit to every stakeholder of the mitigation process. And I want to make sure we cover off on some of the reasons for that. I also want to go through some psychrometric exercises and make sure that we understand how to put psychrometry to work using some of the most basic things that we would use psychrometry for that really drive home the importance of what psychrometry is. But then I also want to transfer over into some more advanced topics. And when I go into the advanced topics, I'm going to go through them kind of quickly because there's a lot of content today. Having said that, we're going to close the presentation out today with some direction on where you can go on nextgearsolutions.com, webinars, and find the more detailed discussion in some of these more advanced concepts, because many of them are concepts that we have discussed in previous technically speaking episodes. Not all of them, but some of them definitely are. So that's kind of an overview where we're going to go. Let's start with just a quick detailed look at what psychrometry is. To understand what psychrometry is, I first want to talk about what we're trying to accomplish when we say structural drying, right? Restorative drying, water damage restoration, the drying element in water damage restoration. What are we really talking about? So we have a structure, and here's just a really basic schematic of a structure. And we're trying to remove excess water from these assemblies and components, right? And what, to our eyes, what we normally see, we see carpet, we see drywall, we see these types of things. But in reality, what we're trying to dry are building materials at a microscopic level. If we want to understand the physics, we've got to think about it at a microscopic level. So before I get into what psychrometry is, let's just explore this building material microscopically for a second. This would be a sample of wood magnified about 1,000 times. And we can see in this sample of wood that could be a 2x4, it could be some sheeting material, whatever it is. We can see these pores or these cell cavities, and we can see the actual fiber or structural material of this wood. Let's zoom in just a little bit more and really take a look at what this material looks like. This is what we're trying to dry. This is where the water lives. This is where the water exists, at least the more difficult water. This is where it exists. That water is going to fill a couple of different spaces. These little red and white molecules would be a representation of water molecules. A couple of things about this image that I think are really important for you to observe. First of all, notice that the water exists in a couple of different places, right? Some of that water exists in the capillaries or pores or cell cavities. In that area, that water is typically a liquid, right? And that's what liquid water looks like if you were to have a magnascope strong enough, or my microscope rather, strong enough to magnify it. This is what water would look like. It's these little chains of molecules. And notice how these little chains of molecules are moving, right? Unless there is absolutely zero energy, all matter is in constant motion. Usually that motion is this form of kind of vibration or oscillation, if you will, but there's always some motion. That's going to become really critical when we get into psychrometry deeper here in a second. So some of it's in the cell cavities and pores. Some of it, however, is absorbed, right? If you look really closely, you can see there's also some water molecules that are actually in the fiber itself. And these molecules aren't bonded with other water molecules. They're actually bonded to the fiber. They're holding on. There's a chemical bond or a physical bond with the actual fiber itself. And this is a different kind of water. This is what we refer to as bound water, right? It's chemically bonded to the substrate of the material. Both of these are on the menu for drying, right? I have to remove the liquid water, the free water. I also have to remove the bound water, the chemically absorbed water. Psychrometry is a tool that helps me understand the relationship between this gas that is in the air, which would be the right-hand side of the screen, and the moisture that is in this material on the left-hand side of the screen, and how energy and this gas relationship drives something called thermodynamics and equilibrium. Now, those are some bigger terms. We're going to define all of them. But at the end of the day, psychrometry is the ruler that helps me measure the driving forces that cause these two to seek an equilibrium. The goal in drying is to drive that equilibrium in the right direction, right? I want the water in the material to have a driving force that moves it out of the material and therefore leaves less water in that substrate or in that material. Psychrometry allows me to measure those driving forces so that when I make changes or I make manipulations of the environment, I understand if those changes are positively impacting the direction of this water movement or if they are negatively impacting the direction of this water movement. It removes the guesswork. Instead of just saying, well, if I add a dHue, it might work, then coming back 24 hours later and saying I added a dHue and it didn't work, right? Which is not the problem-solving workflow that we want to have here. It allows me to make a change, observe the impact of that change, and then understand the longer-term impact resulted to that change. That's what psychrometry does for me. All right, so this kind of analogy here of taking a look at water and kind of molecular level is going to help as we go through some of this. Before we get into the meat, though, let's get into some definitions, right? We always got to, especially with technically speaking, we need to be technically accurate. So let's make sure that we define a few of the most critical terms related to psychrometry. And there are a few, about 5 here, that I really want to start with, but we're going to get to some more a bit later. The 5 core basic terms that I want to define are psychrometry, right? That's what we're talking about, so let's define it. Thermodynamics, temperature, which sounds like a simple word, but it really isn't. Relative humidity, and humidity ratio. The most confusing part of psychrometry, by the way, is understanding the difference between relative humidity and humidity ratio. So we'll get to those in a second. First, what's psychrometry? Psychrometry is a field of engineering concerned with the physical and thermodynamic properties of gas, vapor mixtures. Sounds simple enough, right? In other words, psychrometry is really just a way for us to measure and understand something. We're going to define thermodynamics here in a second, so we'll know what something is. But that something is related to gas-vapor mixtures. The thermo and thermodynamics should give you a strong clue as to what we're measuring in that gas-vapor mixture. To better understand, it's basically the relationship between the water in a solid or a gas and the energy in that same solid or gas, and how that relates to the tendency for that moisture or that gas, to be a liquid, to be a solid, to take the different states or move from one location to the next. The relationship is all about the matter, in this case water, and the energy. It's a relationship between those two. Digging into that more in just a moment. The literal translation of psychrometry, if you look into the Latin, is psychro, meaning cold, and metrics, meaning measurement. In other words, psychrometry is measurement. A lot of people say that psychrometry is the science of drying. Psychrometry is not the science. Psychrometry is a ruler. That's all that it is. It's a really funny shaped ruler, and we'll take a look at it, but it's a ruler. That's all that psychrometry is. And it doesn't matter how good you are at measuring something. If you don't understand the purpose for measuring it, And how to translate those measurements into action is just a bunch of confusing gibberish, right? Which unfortunately for a lot of people, that's what psychrometry ends up being. It's because they don't understand the value or the purpose of the measurement. So one of the ways to understand the purpose is to understand the term thermodynamics. Thermodynamics is the actual science. It's the branch of physical science that deals with the relationships between heat and other forms of energy. And this science is the true science behind drawing, thermodynamics. We'll expand that as we get a bit deeper into things. Temperature is one area or component in thermodynamics. It's really important to properly understand. Temperature is the measurement of sensible, meaning feelable, right? Feelable heat. Temperature determines the direction energy will move on its own, spontaneously. All right, and I'm going to give you examples of all this in a moment, so bear with me. Just load these into the brain for a second. Good analogy here for temperature, if I've got a standard thermometer, is that if I have a given temperature in one location, and somewhere near or next to that location there is a lower temperature, then energy will flow from right to left, right? That's what that's telling me on the screen, okay? It's just going to move from more temperature to less temperature, more concentration in energy to less concentration in sensible energy, okay? If I have the opposite, we'll get the opposite, right? I'm going to receive energy from higher temperatures. That's always the direction temperature will flow. Quick side note on temperature, because you're going to see it when I go into my psychrometric chart. You're going to see this term dry bulb temperature. And I just want to make sure that doesn't confuse you. A dry bulb temperature is a temperature that is measured with just a regular dry thermometer. There's no water on the end. There's no wet sock on the end. There's actually a thing called a wet bulb temperature. And that's when we put a wet sock on the end of the thermometer, we blow some air across it, and we measure the temperature after the effect of evaporative cooling, right? And we typically get a lower wet bulb temperature and a higher dry bulb. The difference between those two back in yesteryear was how we measured relative humidity. Because the drier the air was, the lower the relative humidity specifically, the lower the wet bulb temperature delta would be, or the greater that delta would be. So what is relative humidity? Almost done with these key definitions. Relative humidity is the amount of water vapor present in air expressed as a percentage of the amount of water vapor needed to saturate that air, right? In simple terms, it's a percentage of the air's ability to support water at that temperature. The more temperature there is, the more energy there is, the more water vapor the air can support, right? The colder air is, the cooler its temperature, the less energy there is, the less water vapor we can support. Remember, it's all about that energy relationship, all right? Here's a couple of analogies to help you understand what relative humidity represents. If I have a measuring cup, and this measuring cup is half full, that would be like saying the relative humidity in an air sample is 50%, right? I don't know how much water is in the cup. I don't know if it's a half a cup, a full cup, 3 ounces, 10 ounces. I have no idea. All I know is the cup is half full. That's what we're saying when we say relative humidity. If I say that the air is at 50% relative humidity, you don't know how much water is there. You just know the air has 50% of the water content that the current energy can support. That's all you know. Increase the energy, you can support more than that, and your 50% relative humidity goes out the window, right? In other words, 0% just means there's no water. 100% means we're using all of the available energy. We're 100% of our capacity. 50% means half full. The problem with relative humidity is you can't make comparisons from one air sample to the next or one time to the next time using relative humidity alone, right? In this analogy, I've got a cup that's at 50% relative humidity, or 50% full. I got another cup that's 100% full. So the question is does the cup with 100% have more water in it than the cup at 50%? Well, maybe, maybe not. I don't know because they're different sizes, right? More energy is a bigger cup, less energy is a smaller cup. So if we were to overlay over that some actual measurements of true water content, whether that's cups of water or whatever it is, let's say it's cups, then the one that's 50% full is holding on to 2 cups. The one that's 100% full is holding on to 2 cups. So guess what? They're holding on to the same amount of water, even though one's half full and the other's 100% full. This is the reason why we need a measurement other than relative humidity to truly understand how much water is in air. We need something that's like cups, right? Like ounces, like pounds. So we use humidity ratio to get a better understanding, okay? All right, So again, just another analogy here, even if you had two air masses that were both at 50% relative humidity inside and outside of a building, for example, that doesn't necessarily mean that they're holding on to the same amount of water vapor. If inside the building is 80 degrees, then 50% full is going to be a lot different than outside if we're at 50 degrees, right? 50 degrees is a smaller container. It has less energy, can support less water vapor, all right? So humidity ratio kind of solves that quandary for us, solves that problem. Humidity ratio is the weight of water vapor in a given weight of air. So to understand that, let's use kind of a little mathematical analysis here. Humidity ratio expresses the weight of water vapor compared to the weight of all of the other stuff that makes up air, quote unquote dry air. In other words, the argon, nitrogen, carbon dioxide, and all the other gases that are not water, aka dry. We can measure the weight of each of these in imperial scales and metric scales. If we were in metric, we'd measure the water vapor in grams for every X kilograms of everything else, right? So it'd be grams per kilogram of dry air. But we use grains. In the imperial measurement, at least, we use grains. So grains of water per pound of air. To understand this measurement, we gotta kind of dissect what a grain is. Let me kind of define for you what the unit of measure is. A grain is a 7,000th of a pound, right? There are 7,000 grains. It's just a unit of measure per pound. It's like there are 12 inches in a foot. It's just a unit of measure. That unit of measure has a history. It comes from literally grains of wheat. Way back when things weren't quite as sophisticated, it actually originated in the Mediterranean with traders, they would use kernels of wheat to measure things that did not weigh very much to determine if this was more gold or less gold, right? Or more silver or less silver, or whatever else they were trying to measure. So it's just a unit of weight that used kernels of wheat as the unit of measure per pound. So we measure grains of water per pound of air. And pound has kind of a very similar origin, by the way. It actually comes from the Libra. That's why we use LB as the abbreviation if you ever want to use that for a trivia question one of these days. But they usually literally use a certain size of rock to represent the pound. So grains of water per pound of dry air is the specific measurement. And the nice thing about humidity ratio, whatever the scale is, grains a pound or whatever else, or per pound, in order for grains to be higher, the water has to weigh more. And there's only one way to make the water weigh more, and that's if you have more, if you add more, right? And the opposite is also true. If it's lower grains somewhere, there is less water in that location. If the grains are lower today than yesterday, there is less water in the air today than there was yesterday. It doesn't matter what temperature is doing, right? That doesn't impact that. So the abbreviation is GPP. As an example, if we had 55 grains per pound, then what you literally have is 55 kernels of wheat worth of weight of water vapor in every pound of dry air. Incidentally, if you're curious, a pound of dry air is about 14 cubic feet. It's about the same size as a 4-drawer filing cabinet. That's what a pound of dry air is in physical space, right? So if I've got 55 grains and I've got 55 7,000ths of a pound in every 4-drawer filing cabinet that would fit inside that space. That's what it physically means. So how much water is that? 55 grains per pound? We just kind of walked through that. If I go back to the measuring cup analogy here, if I have one cup that's at 50% full, the other cup is at 75% full. Again, if that's all I know, I don't know which cup is containing more water. But if we put grains on the cup, and we're measuring now the amount of water by grains and how much the water weighs, and one cup's holding on to 20 grains because it's 50% of 40, that's its capacity, and the other one can hold 20, but we're at 75% full, that'd be about 15 grains. Now we can compare the two, and we can figure out which one has more and which one has less, all right? And that's one of the key drivers in psychrometrics is just bringing it down to that simple metric or that simple measurement so we can make some really basic drying decisions. So with all that said, those are the definitions. We can finally get into the psychrometric chart. All right, so like I said, psychrometry is just a ruler, right? That's all it is, metry, measurement, psychrometry, right? So this is what the psychrometric chart looks like. It is a ruler, it's got a funny shape to it. So let's understand the ruler, understand a couple of measurements, and then get into what really matters, some psychrometric exercises and putting it to work. So to understand the psychrometric chart, we got to kind of break it apart here and understand the parts and pieces. The very bottom of the ruler is temperature, dry bulb temperature, right? Which means just normal standard thermometer temperature. A psychrometric chart can have different temperature ranges depending on what you're using it for. A pretty standard temperature range for charts in our industry is about 20 degrees Fahrenheit to about 120 degrees Fahrenheit. But you can get psychrometric charts with any temperature range, right? You just look them up online, you can find them all over the place. So that would be the dry bulb temperature. On the far right-hand side, there can be many different scales or rulers on the far right-hand side. The most important one is the actual water content of the air, or grains per pound. Right, depending on your temperature range, how high that number is going to go up, the chart is going to vary, right? On the middle of the chart and the far left-hand side are the curved lines that represent relative humidity, all right? So that curved line on the outside of the chart is 100% relative humidity. If you take a look through the middle of the chart, you'll notice that we have 0 at the bottom, 10, 20, 30, 40, 50, etc. across the middle of the chart. Now, the reason the chart looks this way, if you look at cold, 20 degrees Fahrenheit, right? That's not a lot of energy. So at 20 degrees Fahrenheit, the ability for air to support water is very, very minute. But as we increase temperature, we're increasing that sensible heat. And as we increase that sensible heat or energy, the ability for air to support water also increases. And that's the reason why the chart has an incline as we move up the temperature scale. It's because we can support more water with warmer temperatures in that air mass, all right? 100% relative humidity, again, would be that very last far left curved line. That's the saturation point at the edge of the chart. So let's take a look at an example, really basic example here. Let's say that we had air that was 50 degrees Fahrenheit, right? Notice where at the bottom of my chart here, I've got my temperature line. See where the 50 is. That line that goes up from 50 represents 50 degrees Fahrenheit, that whole line there. If that 50-degree air was also at 50% relative humidity, then I would find the curved line through the middle of the chart, and your chart will typically have a relative humidity label on it that'll say 50%. Where those two cross or intersect on the chart, we move immediately to the right, and we find out on this ruler, what does that mean for the amount of water? All right, in this case, 50 degrees and 50% represents 27 grains, 27 7/1000ths of a pound of water, all right? Not a lot of water, but it's water vapor in the air. Now, to really test your understanding of the chart, if 50 degrees Fahrenheit at 50% relative humidity is 27 grains, then what is 50 degrees at 100% relative humidity? And think about that for just a quick second, without even looking it up on the chart. If half full is 27 grains, you should be able to figure out in your brain, without even looking at a chart, that 100% full would be twice that, exactly twice that. And that would be exactly correct. So twice this, 50 degrees Fahrenheit at 100% relative humidity would be 54 grains. Don't even have to look that up on my chart. If I know that 50% is 27, but I know that 100% is twice that, right? In fact, I could also do the opposite. If 50% full is 27 grains, then 10% full would be 1/5 of that, right? Looking at 25% full would be half of that, right? So it's just a percentage, right? That's all that relative humidity is. It's just a percentage. So 100 degrees and 50%. Let's do the opposite now. Let's take it to 100 degrees Fahrenheit. So raise the temperature and go to 50% relative humidity. 100 degrees Fahrenheit at 50% relative, where the two intersect on the chart, we go to the right, we get 146 grains, all right? Now notice that my chart caps out at 200. That doesn't mean that's all the water that the air can hold. It just means I ran out of paper. I ran out of screen, right? So my chart just kind of caps off there because I need a really tall screen to get all the way up to 100 degrees at 100%. But if you use what we just talked about, you can figure out what it is. If 100 degrees at 50% full is 146 grains, then 100% full is twice that, right? 100% full would be 292 grains, right? So that if you understand that conversation, then you understand how the psychrometric chart is really put together. And that's the reason why I go through that analogy, okay? So there are other things that we can calculate on a psychrometric chart if you get a more advanced chart. Some of these we're going to talk about today, but things like enthalpy and BTUs per pound of dry air, dew point, vapor pressure, these are other properties that are typically on this ruler. And in some cases, they can be quite handy and quite useful, especially dew point and vapor pressure. And we'll touch a little bit on why towards the back half of the presentation with some more advanced conversations. But 90% of what you need to understand, 90% of the decisions that you're going to make will relate to what we just talked about. All right, so that kind of gets us through the basics of the chart. Let's apply some of the basics of the chart. Again, this is a great point for me to give you a reminder, by the way, because I only see one question dropped into the Q&A area. At any point as we're going through today, if you've got a question, drop it into the Q&A area so that at the end of the presentation today, we've got that kind of preloaded and we can go through some of those questions. So don't hesitate to drop a question at any point. So now let's get into some basic applications with psychrometry. When I measure with a thermal hygrometer in my drying environment, the most basic measurement that we typically see made is somebody walking into the environment. So we have, Pat or Joe or Chris, the technician, walks into a drying environment. They stand in the middle of a room. They hold out a thermal hygrometer and they measure the air in the middle of that drying chamber or that drying space. All right. And here's what they may find. Let's just say, as an example, they find that it's 85 degrees and 23% relative humidity on their thermal hygrometer. All right. Just to get a quick chart practice in, that would be, again, 85 degrees, 23%. We'd find where the two lines cross, move immediately to the right and find that we're at about 40, 42 grains per pound, 41 grains per pound, somewhere in that neighborhood. Okay. Plus or minus a 7,000th of a pound is close enough, by the way. All right. Horseshoes and hand grenades. All right. So 41 grains. So what does that mean? What does that tell me? This is the part that really derails a lot of people with psychrometry. I just took my measurements, 85 degrees is 23%. I got on my chart, I found out it was 41 grains. That's what Brandon told me to do. And now I'm looking at 41 grains, scratching my head saying, what does that mean? Okay, my simple answer is it doesn't mean anything. Not by itself. It means absolutely nothing. So when you look at that number, if you don't have answers popping to your brain, you don't suddenly feel like a drying Godzilla, don't feel alone, all right? Because nobody would. By itself, any single measurement means absolutely nothing. It doesn't matter what you're measuring, right? You could be talking about financial measurements. If I tell you right now you've got $5,000 in your bank account, that doesn't tell me how financially strong you are or how financially stable you are. But if I measure yesterday and I measure today and I measure 2 weeks from now and a year from now and I watch the trend of that balance, now I know how financially stable you are, right? In other words, it always takes more than one measurement. It doesn't matter what you're measuring to make sense out of that measurement. You need more than one. So by itself, 41 just tells me that there are 41 7,000ths of a pound of water in every pound of dry air within the space sampled or measured. Sounds really fancy, right? Sounds really, really complicated. Gives me a headache just saying it, but it doesn't tell me anything. So not a lot of water, but what does it actually mean? To understand what it means, we need another measurement. So we just took a measurement of the air. Think of that air like a sponge, 3-4 feet above the wet, drying, and evaporating surface. Now let's take another one down at the surface, right down near the surface. I'm not talking about containing the hygrometer to the surface with plastic and all that kind of jazz. I'm just talking about holding your hygrometer right near the surface, down near the floor, and finding out where you're actually trying to dry, what are the conditions there? And we find out that down near the floor, it's 72 degrees at 65% relative humidity. Well, don't even go to the chart. Not yet, at least. Just look at the air 3 feet above the floor versus the air right near the floor. And I see all kinds of red flags, right? The air near the floor is the air doing the work, right? That's what's actually drying the floor, and that's at 72 degrees. 85 is more energy, all right? I would like to get that energy in the material because that's where I'm trying to dry. But down near the material, I'm only at 72. This tells me right off the get-go that my air movement is insufficient. I do not have enough circulation, right? If I had enough circulation, I'd be at 85 down near the surface. I also see a 65% relative humidity. The air down near the surface, especially because it's cooler, is holding on to more of its capacity. There is less free available energy to take water from the building material because that cup is 65% full. It's like a bus coming up to a bus stop that's already 65% full. You're not going to take a lot of passengers, right, from that bus stop if the bus is already 65% full. It'd be much better if the bus showed up 23% full. A lot more open seats, right? So I can transport more water away from that evaporating surface. Right? It's a really simple analogy, but it's 100% technically accurate. Okay. But if we go further and we take a look at our psychrometric chart, we'll find out that the temperature here isn't the only problem, right? The grains are also the problem. Down near the surface, we're at 78 grains per pound. Up above, we're at 41 grains per pound. This is further evidence that your air movement installation is failing you, all right? It has not been installed properly. 78 grains is a weight. That weight exerts a pressure, right? And without even getting into vapor pressure, just think about the simple logic. If the water vapor weighs more, it's exerting more pressure on the surrounding environment. The water vapor trying to come out is being resisted by that additional weight. I would much rather have 41 grains of resistance or weight than 78 grains, nearly twice that at the wet evaporating surface. This is going to cut your drying time, or double your drying time rather, of this environment. It's going to double your drying time because you have nearly double the weight at the surface. An additional air mover getting better airflow would cut your drying time in half. That's literally what this means. So again, the reason for diving into this so deep and stepping up on my soapbox and kind of preaching this part of it is this is the most basic part of psychrometry, right? The most basic part of psychrometry. And just look at how telling and how exact and how absolute this information is to help me understand the most basic piece of equipment installation, an air mover, right? I'm not guessing. I know exactly what's going on in this scenario. I know this area is going to take twice as long as the other areas where I have better airflow. This is going to be my problem spot, right? This is the one that's going to take me 5, 6, 7 days when everything else took 3 or 4 days, right? So psychrometry, that's the value behind psychrometrics. Measure twice is the principle, right? And surfaces also matter. As an industry, we do not take nearly enough measurements down near the surface of building materials with our psychrometrics. Here's another great example of something also very, very similar with basic psychrometrics. Now let's take a look, instead of taking a look at the vertical here, let's take a look at the horizontal on a schematic of a few rooms in a drying chamber. John, Joe, Chris, Sue, Sal, the technician, whomever they are, goes into the corner of a room here. They take a measurement and they find out that we've got 85 degrees and 23% relative and 41 grains in this part of this drying chamber. So again, I asked the question, what does that mean? What does that tell me? And remember the same conversation we had a second ago. It should feel like deja vu. It tells me nothing, right? By itself, it tells me nothing. Congratulations, there are 41 7/1000ths of a pound of water for every 14 cubic feet of air in that corner. Doesn't tell me anything. I know it sounds fancy. I need a second measurement. In order to understand the value of any metric of any sort, we need two. The second measurement might be in an opposite room in the same drying chamber, and find out there that we're at 78 grains in the other end of my drying chamber. Again, this is another example of air movers failing you, right? Your installation has not effectively created circulation from room to room. My theory would be is that you've installed the dehumidifier in the room in the far left. That's probably where that dehumidifier is situated, but you have not installed air movement to properly circulate the air between those rooms and ensure that that dehumidifier is equally affecting all of those spaces, okay? There was a great Technically Speaking episode specifically on maximizing air movers, by the way. If you're having challenges getting universal readings throughout your drying chambers, watch that episode on maximizing airflow technology, because I go through a really good basic principle on how to install air movers properly and ensuring you're getting that proper circulation. One more example on this. Let's, instead of taking a look at physical space, let's look at time. If I take time here, where I've got the amount of water vapor in the air over time in a drying process, if I take a reading at one point in time and get 41 grains, I don't know how well we're controlling the environment. If I take another measurement at a later point in time and we find out that we've got an increase in grains over time, whatever that length of time is, right, I know I don't have control of the environment. If humidity is increasing over time, what that basically means is that my rate of evaporation within the environment is greater than my rate of humidity control within that environment, right? Evaporation is happening at the greater rate. That's what that translates to. That could mean lots of different things. I'm not going to go into the detail behind all of this in this particular episode because we need to get into some other concepts. But I will share this. When your rate of evaporation is winning out and humidity is increasing over time, do not immediately go to installing a bunch of dehumidifiers. That is fixing the symptom. It's not fixing the problem. For example, what if the problem is that you're having intermittent operation, meaning the homeowner's turning off your equipment when you're not there? Adding more dehumidifiers doesn't fix that, right? What if the problem is that there's a water source you didn't identify and there's more moisture in the environment than you're aware of? Adding dehumidifiers doesn't fix that, right? What if the problem is you're having mechanical failure in the dehumidifier that is installed? Adding more dehus may fix that, but it's not the right solution. It's replacing the dehumidifier that's having the mechanical issue. Drill down to find the reason why evaporation is winning out, then fix the reason it's winning out. Solve problems, don't solve symptoms, right? One of my favorite phrases in this industry: solve the actual problem, don't solve the symptom. And always drive yourself. The way that I go about ensuring that I'm solving problems and not symptoms is I always ask the question why at least 5 times. All right, my humidity is increasing over time. Why? Because evaporation is stronger than my dehumidification. Why? If you do that to yourself and ask yourself that question why at least 5 times, you'll be amazed how much more effectively you're drilling down to the core problem instead of applying something to a symptom. Don't solve symptoms, solve problems. I hate it when doctors do that and treat symptoms and they don't find the problem. It happens more often than not. All right, didn't mean to offend any doctors, by the way. All right, so kind of reviewing the basics. Measurements by themselves mean nothing. It all happens at the surface. So think about those surface measurements. If that's not something you're doing today, think about adding that at least in a few locations throughout the project. You don't have to take 500 surface measurements, but I would at least take a couple, maybe at least one for each type of building material. And translate surface, by the way, to where evaporation is happening. So sometimes that means inside of the cavity, right, as a good measurement to find out what's happening inside the cavity, where there's water existing inside the cavity versus outside the cavity, to find out if you have enough ventilation of the cavity itself. All kinds of places that you can apply that. Don't solve symptoms, solve problems as another core principle there. And then one core principle we didn't hit on real hard, but I want to touch on it briefly, is you've got to remember that hygrometers are very temperamental. I'll play on words there, but they're very temperamental. Hygrometers are not a device where you pull it out of the box, stick it in the air, turn it on, see the reading, and write it down, right? Hygrometers have to acclimate, right? They have to get comfortable in the space, right? You got to give them time. They've got to come up to temperature. The whole body of the meter has to warm up to that room temperature to truly be effective, which takes time, right? A really good thermal hygrometer, 60 seconds to 2 or 3 minutes, somewhere in that range, as long as the temperature wasn't too extremely different. $200 hygrometer, $300 hygrometer, you're talking about 10 minutes. $20 hygrometer, you're talking about never, all right? So it's really important to make sure you give them the time to acclimate to the space. All right, so that gets us through the basics of psychrometry, all right? And I'm peeking over at my Q&A over here. I still only have one good, strong technical question that's been put into the Q&A. So I'm going to remind you again, drop some questions in there because we're beyond the halfway point here in the PowerPoint. All right, so terms and definitions, I'm going to throw some more complicated definitions onto the mix now. In addition to dry bulb or wet bulb temperature, relative humidity, humidity ratio, there are also things that relate to more technical understandings of heat and energy that you can find on a psychrometric chart. There's a term called vapor pressure that we can find on the chart. Vapor pressure differentials are something we can analyze on the chart. And we have this thing called dew point. So now we're going to transfer from the basic and get into some of the more kind of intermediate and advanced in psychrometry. All right. So for those of you that are going through psychrometry in detail for kind of the first time, if you walk away from today with at least some basic understanding for these terms, and then practice this using a psychrometric chart, then you're going to get a lot out of the next 15, 20 minutes. Those of you that are using psychrometry on a daily basis, hopefully I can give you some really good, strong additional nuggets or tools for your toolbox here. All right, so first let's understand heat, energy, and temperature a little bit better before I get into these more advanced concepts. Again, from the conversation earlier, temperature is the measure of sensible heat, right? It's the measurement of the energy in the air that can be felt, right? So when I'm standing in a room and that room feels warm to me, the reason it feels warm to me is because this is what's happening in the air around you. You have matter or molecules that make up the gas that is in this air around you. That matter or those molecules are in constant motion within that space, right? They're not sitting still, they're moving, right? And that heat that you feel is literally because these molecules are bombarding your surface. They're slamming into you. And the harder they're hitting you and the more kinetic energy, and that's what it literally is, the more kinetic energy there is behind those molecules, the more energy you gain, because when someone hits you, it imparts energy on you. So you gain energy from that air, right? If those molecules are moving really slow and sluggish, then when there's an interaction between your body and those molecules, you actually give up energy to them. There's more energy at your surface than there is in those molecules, and you lose energy to that air. So that air would feel cold, right? So temperature is literally the kinetic energy associated with these molecules that make up a solid surface, a gaseous surface, a liquid substance. It's the energy, the kinetic energy associated with those molecules. So to truly understand that, let's go back to our really simple temperature gauge here. And let's say that these molecules are moving at a certain speed, and that represents a certain temperature. If I increase the speed of those molecules, then I increase the temperature. That's the literal direct translation. Look at these molecules now and how much faster they're moving, how much more energy they're imparting on the surface. That is what an increase in temperature is. Really important to understand that when we get in these advanced concepts. So now let's translate that to a gas in contact with or in communication with a fluid or a solid, right? So now I have these molecules that are zipping through the air, and as they zip through the air, they slam into a surface of some sort. That surface is comprised of molecules, right, or atoms that are making that surface up. As they slam into that surface, they're going to add energy to that surface. The rate of movement or the speed of movement dictates how much energy they will add. Well, evaporation or drying is all about adding energy to these water molecules to the point where they're moving so fast and vibrating with so much energy that that energy overcomes their bonds and breaks the bonds. That's what drives the evaporation process. It's overcoming the bond that that molecule has with something else so that it can break away and join those molecules up above, right? That's what temperature is, right? Temperature is that increase in that vibration, that increase in that movement. And the warmer that material is, the greater the vibration, the greater the movement. And the greater the movement, the more tendency there is for molecules to break free and become a vapor and evaporate, okay? Now, increasing that movement not only is an increase in temperature, but in a sealed environment, it's also an increase in pressure, right? And this is where vapor pressure comes into play. Vapor pressure is the pressure of a vapor in contact with its liquid or solid form. It can be expressed as the force exerted by the vapor or the tendency of the material to change to its vapor state, right? These are all accurate descriptions of vapor pressure. Here's the simple. If I were to take a bunch of water and put it into a sealed container at a particular temperature, then I could measure the pressure inside that container, right? If I increase the temperature of that container, I will increase the pressure inside that container, right? There's a direct relationship. It's called a pressure-temperature relationship. The big part of refrigeration theory and what makes air conditioners work and all that kind of good stuff. But by raising the temperature, I would raise the pressure inside that container. Now, this is important to drying because if the water vapor in a 2x4, which is just a container, if we warm the 2x4, then we increase the vapor's pressure inside the 2x4. And whatever permeability or porosity it has to let the water vapor out, it will exit at a greater rate because the pressure is greater internally, right? So warming increases the pressure. And then nature seeks an equilibrium as water escapes to neutralize that pressure difference. We can actually measure both of those pressures. We can measure the pressure in the container, and we can measure the pressure outside the container and understand the amount of total force that is driving water vapor out. And we'll get to the psychrometric chart here in a second just to take a look at this. But if I have a 1.5 inches of pressure internally, don't really worry about what 1.5 is. Just know higher is more pressure and lower is less pressure, right? Keep it that simple. But if I have 105 inches of mercury in the container and a half an inch of mercury outside the container, then I know which way water is trying to move. It's trying to move out. In fact, it's trying to move out at a force or delta of 1 inch, right? That's the difference. If I make a change in my drying environment and that difference increases, then my drying rate increases. If I make a change and that difference decreases, then my drying rate decreases. And I mean, there have been a lot of different different descriptions put on this, or different tools or different methods for analyzing this. And most of them really make this way too complicated, all right? All I really need to understand is what is my vapor pressure difference? And the greater that number is, the greater my drying rate. The lower that number is, the lower my drying rate, right? All of the things being equal. It's that simple. So let's understand how you would apply that using a psychrometric chart. So taking a psychrometric chart, I measure the vapor pressure of what's in the container by taking two measurements. The first thing I need to understand is how warm is the material. You can take a laser thermometer and measure the surface temperature of the material if you want. That'd be the quickest and easiest way to do it. If you want to get really, really exact, you would actually put a thermal hygrometer probe into the core of the material and measure both temperature and humidity through the core of the material, but you don't really need to. A surface temperature measurement is going to give you enough data to understand what's happening at the surface. So 50 degrees Fahrenheit, let's say, is what we measured. The second measurement you need is a relative humidity. I've got to know not only how warm is the material, but how much moisture is the material trying to support at that temperature? What is the relative humidity? And this is where we've got to get out the fancy little piece of plastic and put the hygrometer under the plastic and contain it to the surface and let it acclimate underneath that plastic. Or if you know the material is sopping wet, just call it 100%, right? If you know the material's got liquid water, you can see that it's visibly wet, call it 100% because it's at saturation, right? And that would be a really quick and easy way to get that relative humidity. Regardless, at 50 degrees and 50%, let's say that's what we measured, we can move all the way over to the far right-hand side of the psychrometric chart. There's a little scale there that says vapor pressure, and we can find out that the material has a vapor pressure of 0.18. Now we just take our standard measurement of the air, near the surface is best, but of the air, and find out what is my vapor pressure there. What's the difference between that and what's in my material? Let's say we measured the air at 80 degrees and 40%. And we got a 0.42 inches of mercury pressure. Now look at this closely. Where is the vapor pressure highest? The vapor pressure in this case is high in the air, 0.42 inches. Look at the material. The material, the water in it only has a pressure of 0.18. What direction is this water vapor trying to move? What will this material do in the next 24 hours? Will it get any drier? The answer to that is that the water vapor is moving into this material. This material is actually going to probably read wetter tomorrow, not drier. And just step back for a second and think about that as a drying Godzilla for just a moment. How valuable is it for me to understand that this building material that I'm trying to dry is actually going to be wetter in the next 24 hours than it will be than any chance that it'll get drier? That's a pretty valuable thing to understand before it happens, right? Because now I can make an adjustment. Now I can make a change. I don't have to wait 24 hours and say, oh, shoot, it got wetter, right? And then react, okay? Without these types of measurements, you're reacting to changes in the environment rather than being proactive, right? So the next question I always get when I show this is that, okay, great. Water's trying to go into the material, so what do I do about it? How do you fix it? Thanks for telling me the problem. What's the solution, right? Well, the solution in this case is understanding that the reason that your material has a vapor pressure of 0.18. The reason it does is because it's 50 degrees and 50% relative, okay? Now, the 50% relative that you took from that material will be 50% no matter what the temperature of the material is. This one's kind of a little bit of a brain teaser at first, so bear with me for a second. The reason the material is supporting a 50% relative humidity is because it in and of itself has absorbed, through absorption, 50% of its saturation, okay? I'll give you an example. Wood has a fiber saturation of about 30% depending on species. At 15% moisture content, 30% of, or half of the fiber saturation, it'll produce about a 50% relative humidity. I don't care what temperature the wood is. If it's at 15% moisture content, you're gonna get a 50% relative humidity because that's half of its fiber saturation. Okay, those are directly related to each other. Now that you know that, if I raise the temperature of my material to 90 degrees, I'm still going to have a 50% relative humidity. But look at the new vapor pressure. Now the material has a vapor pressure of 0.71. Now which direction is the water vapor trying to move? Now it's moving from in the material to out because I raised the temperature of the material and by relation, the moisture that is in it, okay? So, and again, without getting super deep into detail, just think about the value of being able to be this proactive with understanding your adjustments in the drying environment. Not only does this tell me that I'm now moving in the right direction, I could actually use this model to know how warm I've got to get the material, right? How warm does it need to be to move in the right direction? Alternatively, I could use this model to understand how much drier should my air be to get the thing moving in the right direction, right? If I can't make the material warmer, then I've got to make the vapor pressure of the air lower, right? That's my other alternative option. Maybe in this case, if I can't make things warmer, what I've got to do is move to a desiccant, right? So that I can get the lower vapor pressure needed to move things in the right direction. Okay, so that's vapor pressure and the way that vapor pressure plays into the more advanced, more prescriptive drying process. Okay, and this can be applied in a lot of different places. You know, we could use this measurement to understand what's happening in interstitial cavities and voids, what's happening between multiple layer assemblies, what's happening when I've just got a surface that's being stubborn, inside of built-ins and cabinetry where I've got air spaces that I can measure in versus the air that's outside of those spaces. There's lots of different places where we can apply this, where we take more than one measurement, understand the differences in these measurements, understand if we have appropriate circulation, and then by association, understand what's happening with the material itself by taking those surface measurements and understanding pressure differentials. Lots of places that we can apply this. The last concept I want to touch on here before we start rounding things out and getting into the Q&A, dew point temperature. Dew point temperature, by literal definition, is the temperature at which air becomes saturated with water vapor. Remember the measuring cup, right? That cup, if it's a 4-cup measuring cup, it can only hold 4 cups, right? It has a saturation point. The saturation point on my psychrometric chart is the far left-hand side. That's the saturation point, that curved line right underneath the word relative humidity here on the screen. So what is dew point? Now that I've gone through the definition, what is it really? To understand that, let's take a look at a condition here. 80 degrees Fahrenheit. All right, 80 degrees Fahrenheit on the psychrometric chart. The whole line represents 80 degrees. Let's say that we currently have a 40% relative humidity, 80 degrees, 40%. Where these two intersect on the chart, if I move all the way over to the right, there typically will be a dew point or DP scale on the right-hand side of your chart. That DP scale in this case says about 54 degrees. Kind of notice where I've highlighted it there on the screen. Okay, well, that's great. I got a 54-degree dew point. I still don't understand what that means. Here's what it means, right? Imagine that 80-degree air as a measuring cup for just a moment, okay? The gray shaded area or the white shaded area at the bottom of my chart is the actual water that's in that air. The actual water is about 60 grains per pound, right? That's the actual water content. Notice that that's, if you move to the left-hand side of my chart, that's going to be a different relative humidity depending on the temperature of my air. Let's move from 80 degrees and then step down to 70 degrees, right? At 70 degrees Fahrenheit, notice it's no longer a 40% relative humidity. We've crossed the 50% relative humidity line, and now we're at about 60% relative humidity line. In other words, as I make the air cooler, the chart gets smaller. And that same amount of water is now filling a greater percentage of the chart. If you move all the way down to 55 degrees, notice that that amount of water almost completely fills the chart. And right at about 54, we're at saturation. What this means is that if we get any colder than about 54 degrees, in fact, if we drop it all the way down here to about 40 degrees, that amount of water no longer fits on the chart. Guess what happens to that water, right? That water is going to settle out of the air. It's going to condense. We actually refer to this as degrees of dehumidification or degrees of condensation, right? So dew point temperature helps me understand when I have temperature differences throughout space, in real basic terms, where those lower temperatures may be a problem. If you've got 80 degrees and 40% humidity in a drying environment in the middle of December in Utah, right? And you've got exterior surfaces that are at 40 degrees Fahrenheit on the inside, but I know what's going to happen the next morning. You're going to come back to a bunch of water sweating out on those surfaces, right? That's what this tells me. It tells me that if my air cools below 54 degrees, it's going to condense onto those surfaces, right? It also tells me something else though, and here's the more advanced concept with dew point. Notice the further you go below dew point, the more condensation will occur. And if I cool it down to 30 degrees, I'm going to lose even more water. If I cool it down to 20 degrees, I'm going to lose even more water. Well, the nice thing about physics is that when you do the opposite thing, you get the opposite result, right? So if being below dew point at the surface drives condensation, guess what being above dew point drives? If my surface is warmer than dew point, then I have the ability for not condensation, but the opposite, evaporation. In fact, the warmer I am above dew point, the more evaporation I can achieve. This region of the chart is referred to as the degrees of evaporation. Now, I'm going to give you a rule of thumb. When you are drying building materials and you know what your dew point is, 80 degrees, 40% relative, dew point is 54. Just burn this into your brain. Every surface you're drying should be at least 20 degrees above that dew point. In other words, if my dew point is 54, every surface you are drying needs to be at least 74, 20 degrees above dew point in order to get a healthy drying rate. More would be better, right? With limits, of course, you don't burn the house down, but 20 degrees is your minimum. Be 20 degrees above dew point. And if you can't get the material warmer, lower the humidity in your air, which will lower the dew point of your air, right? But delta should be 20 degrees. That delta should be 20 degrees Fahrenheit. Okay, that's the goal. All right, so that wraps us up on running through psychrometry. It looks like just about in perfect time. I've got 4 questions in the Q&A, 4 questions. I know you guys can throw more at me, so drop some more questions in the Q&A. I'm gonna go ahead and round things out here. It's gonna take me just a couple of minutes to wrap up the actual webinar, then we're gonna jump into the Q&A session. So real quick review. With advanced psychrometry, a couple things I want to drive home. First of all, use the chart, use the chart, use the chart. The more you play with a psychrometric chart in the field, and I don't care if you've got an app that gives you grains, you got a hygrometer that calculates it for you and all that kind of wonderful stuff. That's lovely, but it also makes us quite lazy as it comes to thinking about psychrometry. Take a psychrometric chart, laminate it, put it in your inspection kit, grab a dry erase marker, and when you're in the field taking readings, take a few of those readings and plot them on the chart, because the chart illustrates the relationships. And I guarantee you that if you use a chart for just a couple of minutes a day, that's all it takes, just a couple of minutes a day, not with every reading, just a couple of minutes a day, all right, then you are going to begin thinking psychrometrically. If you're relying on your applications and your calculators and things like that to do all the work for you, you're never truly going to get it. All right, you have to look at it on a chart and plot more than one reading at a time. Plot a reading on a chart and then plot a second reading on a chart and compare them. So what's different? Why is it different? How is it different? And what does that mean? What's going to happen next? And when you do that, you'll begin to think in terms of psychrometry. Remember that heating happens in contact, right? If I've got warm air and a cold surface, then the air near the surface is going to be cold. Air movement to drive that heat where it actually needs to be, right? And the only way I'm going to make the water warm is if the material's warm. If you got a cold material, you got cold water. You got cold water, you don't have a lot of energy. If you don't have a lot of energy, you're not going to have a lot of evaporation. Vapor pressure drives the process, right? If vapor pressure differentials are high in materials and low in air, we're moving in the right direction. The greater the difference, the greater the movement, right? And then last but not least, 20 degrees of evaporation. That's the target, right? 20 degrees of evaporation. So 20 degrees above your dew point. Okay, so that wraps us up on Technically Speaking, episode number 8. I'm going to go into Q&A here in just a moment, so stick with me. But let me go ahead and close out the recorded portion of this that will be available after we're done today. Again, my name is Brandon Burton, Senior Principal of Industry Relations at CoreLogic, also the Chair of the ANSI and ICRC standards. Don't hesitate to reach out to me for anything that I can do to support you and your water mitigation business. I'll give you my email here in just a moment. Next up on Technically Speaking is going to be episode number 9. We're going to go get underneath the building and talk about substructure mastery. If you deal with a lot of crawl spaces and basements and things like that, this is the episode that you're going to want to catch, because we're going to get really specific into some tips, techniques, secrets, etc., as it relates to dealing with substructures. By the way, if you want to go back and view any of the previous episodes, www.nextyearsolutions.com, go into webinars, and you'll find all of the past episodes that we've done for Technically Speaking on the Restoration Webinars page. So everything's there. You can replay those webinars. And if you missed those webinars and still want your ICRC continuing education credits, you can actually still get them for those past webinars by jumping in there and watching those.